geobyte.
Similarly, let us take the another important problem. Okay, look at the screen. It is asking like this. In which of the following process heat is neither absorbed nor released by a system? Only adiabatic system. Okay, so adiabatic system means the system in which the heat transfer is zero is called adiabatic system, or the process in which the heat transfer is zero is called adiabatic process. Right, let me write that point. Okay, the system in which heat transfer is zero, heat transfer is zero, is called adiabatic system. Adiabatic system. Similarly, I can also write like this. The process in which heat transfer is zero, heat transfer is zero, is called adiabatic process. That means adiabatic system means it is insulated system. Okay. Anyhow, option B can be selected. Okay. Similarly, let us take the another important problem. It is asking like this. The volume V of a monatomic gas varies with its temperature T as shown in graph. Look at the volume versus temperature graph. Here it is clearly given for the process AB, volume is directly proportional to temperature. So for any ideal gas, volume is directly proportional to absolute temperature only at constant pressure. That means the process AB marked in the VT diagram is isobaric process. Isobaric process or constant pressure process. Okay. The ratio of work done by the gas to the heat absorbed by it when it is undergoing a change from state A to state B. What is the ratio between the work done and heat transfer? Okay. For that, as you know, at constant pressure, at constant pressure, work done equal to work equal to P into V2 minus V1. Can also be written as PV2 minus PV1. Since we are discussing the constant pressure process where P1 equal to P2 equal to P. Therefore, it can be written as P2 V2 minus P1 V1 because pressure remains same. Can also be written as nRT2 ideal gas equation minus nRT1. It is equal to N into R into T2 minus T1. That is the work done formula. Similarly, as you know, heat transfer Q equal to formula N into Cp into T2 minus T1. Okay. Then work by heat equal to N into R into T2 minus T1 divided by, that is the work now, Nr T2 minus T1 divided by N into Cp into T2 minus T1. Okay. Here this N is cancelled. Similarly, T2 minus T1 is cancelled. Finally, it is R by Cp. R by Cp. As you know, Cp minus Cv equal to R. Right? From this, let me write the Cv outside. Cp by Cv minus 1 equal to R. Cv, Cp by Cv equal to gamma minus 1 equal to R. From the Cv equal to R by gamma minus 1. Then Cp equal to what? Gamma Cp. Gamma in Cp equal to gamma Cv. Cp equal to gamma Cv. Gamma into Cv r by gamma minus 1. Okay. Let me write that value. It is equal to r by Cp. Gamma r by gamma minus 1. This r is cancelled. R is cancelled. Finally, it is equal to gamma minus 1 by gamma. But what is the name of the gas given? Monatomic gas. For monatomic gas, as you know, for monatomic gas, gamma value equal to 1.67. So it is equal to 1.67 minus 1 by 1.67. It is equal to 0.67 by 1.67. It is equal to 2 by 5. That is approximately equal to zero point 0.4. 0.67 by 1.67 is zero point 0.4 equal to 2 by 4. Look at the options. 2 by 5. 2 by 5. Right? 2 by 5. Look at the options. Option C is absolutely correct. Okay? Na? Yes. Similarly, let us take the another important problem. It is asking like this. The efficiency of an ideal heat engine working between freezing point and boiling point. Okay, as you know, freezing point of water equal to 0 degree centigrade. It is equal to 0 plus 273 is equal to 273 Kelvin. Okay. Similarly, boiling point of water, boiling means boiling temperature of water, boiling point of water at atmospheric pressure equal to 100 degree centigrade equal to 100 plus 273 is equal to 373 Kelvin. Okay. Here ideal heat engine cycle efficiency means Carnot cycle efficiency. Carnot cycle efficiency equal to 1 minus the minimum temperature in Kelvin by maximum temperature in Kelvin. 1 minus minimum temperature 273 by 373. It is equal to 0.268. To get in percentage, multiply with 100. Multiply with 100. 26.8 percentage. That is the ideal heat engine cycle. Ideal heat engine cycle efficiency for the temperature limits of freezing point of water and boiling point of water. Look at the option C. Option C is absolutely correct. Okay. Are you following clearly? Yes. Similarly, let us take the another important problem. Look at this problem. It is asking like this. Thermodynamic processes are indicated in the following column. Process 1 P, Q process 2, process 3 R, S for process 4. Look at the process 1. Look at the process 1. Process 1 is marked with P. Process 1 is constant volume process. Constant volume process. That means P, constant volume is isopole. PC correct. PC correct. Similarly, process 2. Process 2. Look at the process 2. I can mark it is constant. No, among the 3 and 2, 2 is maintaining more slope na. So therefore it is adiabatic process. Adiabatic process. So this adiabatic process is marked as 2. That means adiabatic process is marked as 2. Right? Q2 correct. From this I can write the Q2. Here P, C correct. Q2 correct. Q, Q2 means adiabatic na. Adiabatic is A. Right? QA correct. QA correct. Then process 3. Process 3. It is isothermal. Isothermal process. Isothermal process. Right? Process 3 R. or isothermal or D, and process 4 isobaric in the PV diagram. Process 4 isobaric. Isobaric means constant pressure. So that is given as B. That means SD. Yes, SB, SB. PC, PC, QA, QA, RD, RD, SB, SB. Therefore, option B is absolutely correct. Okay. Process 1 is constant volume, that is isoporic. Process 2 is adiabatic. Process 3 is isothermal. So, the curved lines may be either isothermal or adiabatic. The curve which is maintaining more slope, right, in the PV diagram is coming under adiabatic process. So, the curve which is maintaining less slope, right, in the PV diagram can be concluded as isothermal process. Horizontal line is representing for constant pressure, that is isobaric, and vertical line in the PV diagram is representing constant volume, that is isocoric. Anyhow, option B is absolutely correct. Understood clearly? Yes.
Geobyte.